So, dear students, welcome to the new lecture of Basic Electrical Engineering. In this particular lecture, we will discuss about the transformer on no load condition. So, this lecture will cover the transformer on no load condition, the basics about that, and the phasor diagram of the transformer on no load condition. And then we will also see few examples related to this particular concept. So, to start with the lecture, so let us see the equivalent circuit of a transformer on no load. So any transformer will be set on no load when the secondary winding of the transformer is not connected to any load. So let us consider a transformer which is connected to some AC supply, and there is a secondary winding. So if the secondary winding is open, so under this particular condition, the transformer is set to be on no load, right? So this one is the primary winding, this is the secondary winding, and no load is connected here. So when there is no load, the current in the secondary winding I2 is 0. There would be certain EMF here. Let us say this is E2. There will be some EMF here also, E1, which is because of self-induction. And then we have the supply voltage V1 and some flux phi, which is flowing in this particular iron core. This is the iron core. So in today's lecture, we will understand that what are the basic parameters associated with the transformer on no load, means when the transformer is not connected to any load, right? So we will see that what is the working, how the transformer operates or work under no load condition. The equivalent circuit of the transformer under no load condition is shown here in figure 1. As you can see in this particular diagram, we have certain parameters written. So all these parameters need to be assumed as or taken as the RMS values, like V1 is the RMS value of the input voltage, and similarly I naught is the primary current under no load. Then E1 is the RMS, and this is also the RMS value. RMS value of the induced EMF across the primary winding, and so on. Fine. So this E2 is the RMS value of the EMF induced across the secondary winding, and this V2 is the RMS value of the open secondary winding, right? Or you can say across the open secondary terminals. Now you can see that this I node has two components here, and we have a circuit drawn here. So this particular circuit represents the core parameters. That means the parameters which are associated with the iron core. So these parameters are associated with the iron core, and what is the significance of these parameters that we will understand in this particular lecture, right? So as you can see here, ideal transformer is mentioned. So this means that the ampere turns at the primary winding is equal to the ampere turns at the secondary winding. The power at the primary winding is equal to the power across the secondary winding. So these are the assumptions basically, and that is why we are taking these assumptions from the ideal transformer. Okay, assuming that this condition or these conditions are true, right? Now, as you can see here, that because the secondary winding is open, this is open, so the current in the secondary winding is zero. That means no current flows through the secondary winding. That is I2 is equal to 0 because secondary is open. Now, when there is no load, no current flowing in the secondary winding, so in that case, in primary winding also, the current that flows will be minimum. So this particular phenomena results in the minimum current to flow in the primary winding. Now, what is the reason behind this? The reason is that because there is no load connected across the secondary, so that means the requirement of the current is minimum, right? And this current will only flow because the primary winding is connected to some AC supply. And this is give the instantaneous value is given by V1 is equal to V1M sine omega t, right? So this primary winding, this current which flows in the primary winding when no load is connected across the secondary is denoted by I naught, and we call this current as no load current, and this current is generally 2% to 5% of the rated primary current. Now, what is rated primary current? Rated primary current is that current which is specified by the manufacturer, means the maximum current that can flow through the primary winding when the transformer is connected to the rated load. And rated load means the load that a transformer can bear and withstand without any damage, without any uh, malfunctioning. Okay, now let us proceed further. Now, as we are discussing that a minimum current is flowing in the transformer even when the current in the secondary winding is zero. So this current I naught is basically responsible for the certain phenomena that occur in the transformer, and you can see here that this current is dividing into two currents across the two elements of the core, this R naught and X naught basically are the resistance and inductive reactance of the transformer core. That means these parameters are associated with the transformer core. And this current I naught is dividing into the two components. One is IW, as you can see, flowing through R naught, and the second component is I mu, or it can also be written as IM, which is flowing through X naught, where X naught is the inductive reactance of the transformer. These all are the core parameters. Are associated with the transformer core, means the iron core of the transformer, because there is no current flowing in the secondary winding, no requirement of the rated current is there. So that means in primary also the rated current will not flow. Yes, it is true, because of the iron, because your primary winding, primary side is making a circuit, right? If you see in a transformer, even if secondary is not connected to the load but primary is connected to the supply, primary is connected to the supply, right? So that means some current I naught will be flowing in this particular primary winding when the secondary is not connected to the load, right? So this current is flowing here, and this current when flows through the primary winding is responsible for the two effects in the transformer core of the transformer basically. And these two effects are symbolically represented by a resistance and by an inductor, where resistance represents the heat effect and inductor represents the magnetization, right? So now these two effects are basically created by this I naught, which is no doubt a negligible current, very low current, but these effects are there present in the transformer, right? Now let us understand what are these effects. So a transformer is said to be on no load when the secondary is open and primary is connected to an alternating voltage, which is V1 in this case. And under no load condition, a minimum current, as I just discussed with you, a minimum current of 2 to 5% of the rated primary current. And rated primary current is always specified by the manufacturer. So we denote this current, which is the negligible current, as I naught, and we call it as the no load current. So this I naught is known as no load current. So when this no load current is flowing through a transformer and it is responsible for certain phenomena, certain changes in the transformer, and as I just mentioned, the first is the heat effect, or we can also call it as The loss means the copper loss which is associated with the primary winding, but it is also responsible for the heat generation in the core, and that heat is generated because of the eddy currents and the hysteresis. That means when this no load current flows through some iron core, this no load current heats up the iron of the transformer. Now it heats up this iron core of the transformer because of the eddy currents which generate in the transformer. And we all know that eddy currents are the circular currents which generate in the ferromagnetic material because of the magnetization process. And hysteresis is also a kind of loss which occurs in the ferromagnetic material because of the magnetization process of the ferromagnetic material. And these two losses appear as the heating effect in the core, and that is why we represent this as a resistance, because it represents I square R loss, right, in the core. And also because this I naught is flowing in the primary winding, so it will create or it will produce a minimum copper loss in the primary winding, and copper loss is nothing but the I square R loss of the transformer, right? Now, okay, so the second component is I mu or I m, which is also known as the magnetization component. So now this no load current, basically, as it is shown in the diagram also, that it is dividing into two components, IW and I mu, or we generally also represent it with the notation IM. M here represents the magnetization. Okay, fine. So this IW is because responsible for the heat effect. This is responsible for the heat effect in the core, and this I mu is responsible for the magnetization of the core. Okay, so now because the transformer works on the Faraday's law of electromagnetic induction, and it is the magnetic flux which links the two windings mutually with one another. So the generation of flux is mandatory in transformer, and the nature of this flux is bidirectional, which we have already discussed in the EMF equation of the transformer in our previous lecture. Now, these two components are the either wattful component or active component, or the magnetization component is also known as wattless component or the reactive component. And as it is written here also, it sets up the flux in the core, so it is responsible for the magnetization of the core. And because of the magnetization of the core, the eddy currents are produced in the ferromagnetic material. The hysteresis are there in the ferromagnetic material, and these eddy currents and hysteresis appear as heating effect, and that is why the core of the transformer, the iron core of the transformer, gets heat up, and it is represented by, symbolically represented by, the wattful component of I naught, and it is IW. And this is the active component because the heat is the uh, you know the effective this is the effective value basically of the current, right? And this IW is the active component because it is actively responsible for the generation of something which is real, the heat effect. And magnetic field, which is virtual and imaginary, right? So it is because of the I mu. Now So let us proceed further and understand the phasor diagram of the transformer under no load condition. Now, as you can see a diagram here, this diagram is this diagram is the phasor diagram of the transformer under the no load condition. Now, because flux is the common parameter here which links the two windings. It is the flux that flows in the iron core of the transformer and links the two windings mutually with one another. The flux flows here. So flux is the common parameter, and that is why we have taken the flux on the x-axis, the horizontal axis. This is the reason. Now, taking flux as a reference, we will draw all other phasors in this particular phasor diagram. So, flux is the common parameter. Flux is because of the magnetizing component of the no load current. It is also represented by I mu, right? Now these two components will be in same phase because flux is due to I mu. It is the magnetizing component which is producing the flux in the iron core, as it is already mentioned here that the magnetizing component or I mu is it sets up the flux in the core. Now, as you can see in the EMF equation, let us go back and see the EMF equation of the transformer. So the EMF equation was, for primary it was EM1 and sine omega t minus pi by 2, and E2 is EM2 sine omega t minus pi by 2. These two are the instantaneous values of the EMFs induced in the two windings of the transformer, right? Now the flux, the instantaneous value of flux is given by phi is equal to phi m sine omega t. So this is the instantaneous value of the flux in the iron core of the transformer. Now, if you compare these two equations with this equation, you will find that E1 and E2 lags phi by 90 degrees, right? So that is why the RMS values, these two E1 and E2 are the RMS values of E1 and E2, and these are shown 90-degree lagging the phi flux. Okay, so E1 and E2 are lagging phi by 90 degrees. So the first thing is flux. Flux is the common parameter. We have taken it on the horizontal axis, and it is because of the magnetizing component of the transformer's no load current I mu, and that is why I mu is in phase with the flux. Then from the EMF equation of the transformer, we have already understood that the induced EMFs lag the flux by 90 degree, and they are shown on lagging 90 degree the flux. Then let us come back to this diagram. In this diagram, if you see, this I naught current when flows through the core of the transformer, it gets divided into two components. And again, I am telling this is a symbolic representation just to signify the effect of this no load current in the core of the transformer, even when the transformer is not connected to any load. Right now, this I mu, this is parallel to supply. Right, so since your this I mu r node is parallel to the input supply, so now r node is parallel, and x node also, x node and r node are parallel to the input supply. As you can see in this diagram, this is parallel to the input, so these two components are parallel to the input supply. Hence IW is in phase with V1. Now why? The question is why? Because IW is flowing through R node, and V1 is appearing across R node. Hence, the voltage and current associated with R naught are V1 and IW. And we all know that in a resistance, voltage and current are in phase, and that is why IW is shown in phase with V1. Now, if we see, you can see here that IM is 90 degree lagging the voltage V1. Why? Now, the current through X naught is IM or I mu, and the voltage across X naught is V1. As you can see here in this diagram, this particular element X naught is parallel to V1. So here also the voltage will be V1, and here also the voltage is V1, right? So now the voltage and current associated with the inductor X naught is or are V1 and I mu or I m. Now we know that now in an inductor the current and the voltage. So V leads the current by 90 degree. We know that in an inductor, the voltage leads the current by 90 degree, and that is why you can see V1 is leading Im by 90 degree. And you can also say that because Im is lagging V1 by 90 degree and it is coming in phase with the flux, you can take it in any particular manner. That is totally up to you, right? So this is the phasor diagram I already mentioned. Now there are two components which are already mentioned in the previous slide. This IW, which is the active component, and this is also known as the wattful component of the no load current. And this can be obtained by using this diagram, right? Now in this IW is, this is your phi naught. So IW is I naught cosine phi naught, where cos phi naught is basically the no load phase difference between V1 and I naught, where V1 is the primary voltage and I naught is the primary current under no load condition, right? Now, so this Im or I mu is also known as reactive component or magnetizing component or wattless component. You can name it any particular component, right? All are true. It is a reactive component because it is responsible for the imaginary or virtual effect in the core of the transformer, and that is the magnetization of the core of the transformer. It is a wattless component because it is a reactive component, and it is a magnetizing component because it is magnetizing the iron core, and it can be obtained from this particular right angle triangle. So this is Im. So Im is I naught sine phi. So here, because as you see that this I naught is the resultant of the two components, right? I naught is the resultant of I W and I mu, right? So it can be obtained by using the parallelogram law of vector addition. So by using that particular law, you will get I naught as under root I W square plus I M square. Now, so I naught and I naught and V1 have a phase difference, which is the no load phase difference, right? Then the power input to the transformer under no load condition. So this is because the power is generally, the power in an AC circuit is given by P is equal to VI cos phi. But here your transformer is not connected to any load. So the no load power will be given by P naught is equal to V1 into I naught, where I naught is the no load current, into cos of phi naught, where phi naught is the no load phase difference. So this cos phi naught is known as power factor. This is primary power factor. Remember, this is primary power factor because the secondary is not connected to any load. So this is the primary power factor under no load condition. Okay. So Now this was the phasor diagram of the transformer under no load condition. So this was the theory about the transformer under no load condition, and we need to remember few things about this, that under no load condition the current that flows in the primary winding is very small, very low as compared to the rated primary current, and as it is already mentioned also that it is near about 2 to 5% of the rated primary current. Since secondary is open, so there is no current flowing in the secondary winding, and hence there are no losses in the secondary winding. But in primary, because some current, a minimum current is flowing, so there will be minimum losses with the primary winding, and these losses are negligible. We can neglect these losses, but the iron core of the transformer will have the two effects, the heating effect because of the heating effect and the magnetizing effect. Both effects will be there because of the no load current. So the heat effect because of the eddy currents and hysteresis and the leakage of the flux in the primary winding, all these effect will be there, and these appear as the losses in the primary winding. We generally call these losses as the iron losses, right? So now let us see a few numericals related to this particular concept of the transformer. So the first example here is a 3300 to 300 volt single phase transformer gives zero point 0.6 ampere and 60 watt as ammeter and wattmeter readings when supply is given to the low voltage winding and high voltage winding is kept open. So now this is a uh, transformer in which the reading of the ammeter is zero point 0.6 ampere. So let us try to solve this particular numerical, right? So the parameters which are given to us are the power, because 60 watt is the reading of the watt meter, that is the power. And as it is mentioned, the high voltage winding is kept open and low voltage winding is connected to the supply. So that means the transformer is a step up transformer, because the high voltage winding is the secondary winding here. So it is open, and the low voltage winding, it is connected to a supply. So this is 300 volt, and this is E2 is 3300 volt. So because the high voltage winding is kept open, so this is a step up transformer. So the power under no load condition is given as 60 watt, and the no load current, because this I note, the zero point 0.6, so I note here is the no load current, which is the reading of the ammeter. So it is 0.6 ampere. Now we have to find out the power factor of the no load current. So the power is given by V1 I naught cos phi naught. V1 is 300 volt, because low voltage winding is connected to supply, that is, this is the primary voltage, and then this is the secondary voltage, right? So generally the notation, this notation represents that the transformer has to be a step down transformer, but since it is mentioned here in the statement, so we will consider this as the vice versa case, that is a step up transformer. Okay, so from here we'll find out the cos phi naught, and it is equal to P naught divided by V1 into I naught. So the value will be 60 divided by 300 into I naught is 0.6. So it is 0.33 lagging. Now why we are writing lagging here? Because because transformer is an inductive device, right? So it will always be lagging, and we have the inductor. We are representing the winding as the inductor. We represent the magnetizing effect in the core as inductor. So that is why the power factor of the transformer is lagging. Okay, now this is the first thing we have to calculate. The second is the magnetizing component we have to find out. The magnetizing component is Im or I mu, right? So Im is basically given by I naught sine phi naught. As you can uh, take this from this equation. Okay, it is written here also. So Im is equal to I naught sine phi naught. So from the trigonometric rule, we know that sine theta is equal to under root 1 minus cos square theta. So Im can be written as I naught under root 1 minus cos square phi naught. So we can put the values here. I naught is 0.6, under root 1 minus 0.33 square, right? So Im will be equal to 0.6 into 1 minus 0.33 square. So on solving this, we get Im is equal to 0.566 ampere. So this is the value of the magnetizing component of no load current. And the third is we have to find out the iron loss component. So iron loss component is Iw, right? So the iron loss component is given by, so it is because Iw. So Iw is uh, I naught cos phi naught. So it is equal to 0.6 into 0.33. So Iw is equal to 0.198 ampere. So this is the answer. Now, if you want, okay, so this can also be calculated by using the relationship, this one. Okay, so we can also use this particular relationship as, because I naught is equal to under root I w square plus I m square. So from here you can find out Iw by rearranging this equation. So it would be I naught square minus I m square. So we can put the values here, 0.6 square minus 0.566 whole square. So this will also give you the same value, 0.198 ampere. So this is A numerical we have taken up, which is related to the no load concept of the transformer. In this, we have calculated all the parameters which are associated with the no load condition of the transformer. So in this way, this is a formula based question and the questions are very easy to solve. We just have to think and apply the basic fundamental knowledge related to this particular concept, and it is very easy for us to calculate the required parameters. So this was all about today's class. Thank you so much.